Let me give you a quick note on parametrizations of graphs, and then also give you a further example. So here's a note. Let's say that we're parametrizing the graph of the function f, where z is a function of x and y. Then our typical way of doing it has been to set x equal to u, y equal to v, and z equal to f of u and v. So when it doesn't lead to confusion, instead of introducing the variables u and v, we'll simply say x equals x, y equals y, and z equals f of x and y as our parameterization. So it ends up looking like phi of x and y is equal to x, y, f of x and y. Now, basically, we're just using the letters x and y instead of u and v. But one of the reasons that it's sometimes nice to use x's and y's is it helps our intuition when we set up bounds for integrals. So we'll see that later on when we do integrals over surfaces. So now let's see if we can parameterize this. Let's see if we can parameterize the cylinder x squared plus y squared equals 9. So the graph looks something like this. Well, here's the problem. This is certainly not a graph over the xy plane, because if I draw a vertical line in the cylinder, it actually passes through infinitely many points. So it definitely fails the vertical line test. It's impossible to write z as a function of x and y. If I tried to write x as a function of y and z, then I'd be applying a test where I drew a line parallel to the x-axis. And notice that a line parallel to the x-axis is going to pass through the back and through the front of the cylinder. So it would cross the cylinder twice. So I can't write x as a function of y and z. I can also see that over here. If I tried solving for x in terms of y, I'd be taking a plus or minus square root. And similarly, this is not a function over the xz plane. I can't solve for y in terms of x and z. So unfortunately, if we want to parameterize this, we're going to have to split it into two parts. So let's imagine cutting along this vertical line above the positive x-axis and the corresponding line back here above the negative x-axis, and use that to split the cylinder into two parts. So you'll have this part over here where y is positive, and then you'll have the separate part over here where y is negative. Now, each one of those taken on its own is going to be a graph over the xz plane. So we could parameterize each of them separately. So later on, if we were going to do an integral, if we wanted to integrate over the entire cylinder, we could carry out the integral on each of these pieces separately and then add the two answers together. So let's call the part on the right S1. So S1 will be the portion of the cylinder where y is positive, and S2 will be the portion of the cylinder where y is negative. Solving for y in this equation, we have y squared equals 9 minus x squared. So when we take square roots, we'll have plus or minus the square root of 9 minus x squared. So either y is the square root of 9 minus x squared, or y is negative the square root of 9 minus x squared. So over here on the right, this is the graph of y equals the positive square root of 9 minus x squared. And over here, y is negative the square root of 9 minus x squared. So let's parameterize those two surfaces separately. S1, where y is the positive square root of 9 minus x squared, we'll have parametrization x equals y equals z equals. Notice that y is written as a function of x and z. There are no z's here. So I could let either x equal u and z equal v. Or if I want to, I can just let x equal x and z equals z. And then y is the square root of 9 minus x squared. If you prefer at this point to write u and v, and to say that y is the square root of 9 minus u squared, that's perfectly fine. So phi1, my first parameterization, says that phi of x and z is x square root of 9 minus x squared and z. And S2, where y is negative the square root of 9 minus x squared, I'm writing y as a function of x and z, so I'll let x equal x and z equal z, and then y is the square root, negative the square root of 9 minus x squared. So phi2 of x and z is going to be x negative square root of 9 minus x squared and z. So if I were to do an integral, I'd do an integral over S1 using this parameterization, a separate integral over S2 using this parameterization, and then add them together. In a few videos from now, when we get to section 11.7, we'll learn how to parameterize using cylindrical coordinates. And not surprisingly, cylindrical coordinates are going to give us a much, much better way of parameterizing cylinders. Just for one thing, we won't have to divide this into two pieces.